Dan Turner, and I'm going to be providing a review of thermodynamics for the Fundamentals of Engineering examination. I'd like to be able you to access me through phone or fax or email, so I'd like to start out by giving you the information on how you can get hold of me. My phone number is 409-862-8480. Fax number 409-862-8687. And if you'd like to contact me by email, my email address is wdt545one@esl.tamu.edu. The ESL stands for Energy Systems Laboratory, and one of the other hats I wear is Director of the Energy Systems Lab at Texas A&M University. We're going to be following the material in the reference manual that's provided for the Fundamentals of Engineering exam. The thermodynamics section includes first law, second law, ideal gas laws, steam tables, cycles, and a lot of information that you'll be required to know to be tested on. And so what I'm trying to do is to work out a review session that will provide you with, I think, a good overall coverage of the types of questions that will be on the exam. We're going to start out talking about ideal gas laws, and we're going to talk about the first law for a closed system, including conservation of mass and conservation of energy. Then we'll get into the first law for open systems and talk about some of the various devices that you're likely to encounter on the FE exam. And in the course of going through the problems, we'll also be working with the limited steam table information that's included in the supplied reference manual. We're going to be covering 5 different cycles. The famous Carnot cycle, which is our ideal cycle that's often referred to as our sort of our highly efficient, highly idealized cycle. The reverse Carnot cycle, which is a refrigeration cycle. We're going to be looking at the Otto cycle, which is a cycle for the gasoline engine. The Rankine cycle, very simple power cycle. We're not going to get into any of the fancy variations on the power cycle, but we'll look at the power cycle and the simple Rankine cycle. And then the reverse Rankine cycle is the refrigeration cycle. So we'll be covering some problems on that. Psychometric chart, we'll just discuss briefly and review you on how to use a psychometric chart. Psychometric relations will also be covered, as well as partial pressures and heat transfer. Heat transfer may be coming as a surprise to you because the heat transfer is not normally considered to be part of thermodynamics. However, in the Fundamentals of Engineering exam, the specifications in thermodynamics also includes heat transfer. So we're going to talk about the heat transfer problems and some very straightforward problems in conduction and radiation that you might encounter on the exam. So let's go ahead and get started on the review. The first thing that we're going to start out with is going to be review of the ideal gas laws. And as we go through the example problems, I've got about, I think, 18 example problems worked out, and many of the example problems have multiple parts. So altogether, there are about 50 solved problems that you will we'll go through on this exam. Now, this is going to be kind of hard to read some of it. I've written too small in places, and so what we'll try to do is to kind of move this around and look at pieces of it on a page. You'll have the notes in front of you, so you'll be able to see everything that in a little bit more detail. First of all, starting out with ideal gas laws, the other thing that I've attempted to do here is locate the page in the reference manual where these equations are taken from, so the ideal gas laws are covered starting on page 43 in the reference manual. First of all, the very fundamental expression on the ideal gas law is PV is equal to RT. Of course, P is pressure, V is specific volume, in this case small v is specific volume, R is gas constant, and T is temperature. The R is defined as R bar, which is the universal gas constant divided by the molecular weight, and R bar is either 8.314 kilojoules per kilomole Kelvin, or it's 1545 foot-pounds force per pound mole degree R if we're working in the English system. Now, pages 1 and 2 of the reference manual, you'll note in there that there are a number of constants and conversion factors provided. Page 52 in the reference manual gives you some molecular weight data and other data for common fluids. Now, this is page 52 in the reference manual, and there you'll see specific heat data and molecular weight data and specific heat ratios, K, including the table, and you'll also see specific heat and density data for some common liquids and solids. This particular page is not in your notes, but it is page 52 in the reference manual, so you will have easy reference to that when you look in the reference manual. Let's talk about another version here of the ideal gas laws, probably the most common version, and that is P capital V is equal to MRT. V is the volume, M is the mass. Of course, temperature is an absolute temperature. This is very important to remember this conversion. You can make some huge errors in your equation if you don't remember to convert to Kelvin or to degrees R when you're using the ideal gas equations. So this is total volume, and this is, of course, mass. And so the ideal gas law can be written as PV is equal to MRT, or you could also, another version that's quite common that'll be useful to you to remember from working out problems on the exams is P1 V1 over T1 is P2 V2 over T2, or if we want to write it in terms of the specific volumes, P1 V1 over T1, P2 V2 over T2, where the small v's represent the specific volumes. And again, a reminder to always convert to absolute temperatures. Okay, continuing on here with some other equations involving ideal gases. Most of the problems now that you're going to encounter on the Fundamentals of Engineering exam involve constant specific heats. Remember, you're only going to be responsible for the material that's included in the supplied reference, and so there are no relations in there where the specific heats vary with temperature, and so you only are going to have to be responsible for these fairly straightforward equations involving ideal gases and constant specific heat. So some of the equations in there that we want to point out in particular, again, we're still in the ideal gas section for in the supplied reference manual. The change in enthalpy delta H is equal to C sub P delta T. Again, C sub P is the specific heat at constant pressure, and that's found on page 52 in the supplied reference manual that we just looked at. Change in internal energy is C sub V, specific heat at constant volume, times the change in temperature, delta T. And then we've got a couple of ideal gas relations here that deal with changes in entropy that come out of the second law, and that is delta S, or change in entropy, S2 minus S1, is the constant pressure specific heat Cp times the natural log of T2 over T1 minus R natural log P2 over P1. There are two different expressions here that can be used for changes in entropy. Be familiar with both of them. In some problems that you will encounter, you may be able to, if pressure, for instance, is constant, or if volume is constant, you want to use the expression that will eliminate one of these terms and save you some calculation time on the exam. So change in entropy can also be determined from the specific heat at constant volume, C sub V, times the ln of T2 over T1 plus R ln of V2 over V1. Now, for some very special conditions, if we have constant entropy or an isentropic expression, then we can write that P1 V1 to the K is equal to P2 V2 to the K, and K now is equal to the ratio of specific heat at constant pressure to the specific heat at constant volumes, Cp over Cv. And so using these expressions, there are two that are normally used, or the most commonly used, to get the relationships between pressure and volume, and that is P1 V1 to the K is P2 V2 to the K, and T1 P1 to the 1 minus K over K. This may not be completely clear that this is an exponent, but it is. 1 minus K over K is an exponent, and that's equal to T2 times P2 to the 1 minus K over K. So these are the common ideal gas relationships that you're going to run into on the exam, and these are ones that you'll have to be familiar with in doing some of the calculations. So let's take our first example, and that is example number 1. We've got a rigid container of volume a half a cubic meter, contains carbon dioxide gas at 5 kilopascals and 17 degrees C, and we want to calculate the mass of carbon dioxide in the container. Now, as we go through these examples, there's one thing that I'd like to go ahead and point out to you, and that is all of the examples that I'm giving to you are provided in metric units. The reason we're doing this is that approximately 90% of the FE exam now is in metric units. The committee that prepares the exam has a charge to convert completely to metric by the year 2002 or something like that, and the committee working on the exam is actually ahead of their time schedule for converting everything over to metric. So if you I guess my advice to you in preparing for this exam is be familiar completely with the metric system and use metric units throughout, because they're the ones that are going to be seen on 90% of the problems on the exam. If you do have a problem that's in English engineering units, there is also an alternate problem that's exactly the same problem in metric units, and so you have your choice of working the exam 100% metric. And so my advice is to go ahead and be familiar with the metric system, make sure that you're familiar with all the constants and conversion factors for the metric system, and for the most part just kind of ignore the English part of the exam, because so few problems are going to involve English units that you're better off just to go ahead and stick with metric throughout. So in this review, all the 18 review problems plus all the sub-problems that are coming out of the examples are all in metric. So that's my advice, is to go ahead and get familiar with that. Okay, so let's go back to the problem. We've got a half a cubic meter of volume that has carbon dioxide in it at very low pressure, 5 kilopascals, and temperature 17 degrees C. We want to calculate the mass of carbon dioxide in the container. Okay, so our solution, we're going to assume that this is an ideal gas, and our solution just set up here, half a cubic meter, CO2 gas, temperature 17 degrees C, pressure 5 kPa. Assume ideal gas conditions. Always remember to convert into metric, so into absolute temperatures, and so the temperature is 273 plus 17, or 290 Kelvin. Since we're working with carbon dioxide, you have to determine the molecular weight, and that can be found on page 52 in the reference manual. And so this plugged directly into the equation. PV is equal to MRT, assuming ideal gas conditions. And so we've got 5 kilopascals times a half a cubic meter volume divided by 8.314 kilojoules per kilomole Kelvin. That's divided by 44 kilograms per kilomole. This is the molecular weight of CO2, and then that's multiplied by the 290 Kelvin, and you come up with an answer of 0.046 kilograms. Sometimes I've included the units in the problems. If it's a repetitive set of units, I haven't included them, but again, a recommendation to use to go through the units and make sure they're compatible. For instance, you've got kilopascals up here and kilojoules here, and so when they're both in the same set of units, then you don't have to worry about that factor of 1,000 that sometimes enters into it if one is in pascals and the other is in kilojoules. So make sure your units are always compatible here when you go through. It's a good idea just for practice to go through, cancel out all the units. We've got Kelvin canceling with Kelvin. We've got kilomoles canceling with kilomoles. We've got kilograms on the bottom here that flips up to the top to give us the kilograms, and then we'll have a consistent set of units. So this is an example of the calculation of using the perfect gas laws of calculation of the mass in a container. Now, what I'd like to do is take another example, take the same example problem, and then we want to illustrate with this some more about the gas laws and also to do some entropy calculations. So example number 2 involves the same amount of gas in the pressure vessel. We started out at 17 degrees C. We're now going to heat it to 117 degrees C, and we now want to calculate the new pressure, and we want to calculate the change in entropy that's involved for this ideal gas being heated from 17 degrees C to 117 degrees C. Okay, so we can go back to our perfect gas law equations. Remember on the previous page we had relation on the gas laws that P1 V1 over T1 is P2 V2 over T2. In this particular case, since we're working with a container that's a rigid container, the volume stays constant. We're not doing anything to the mass of the container or the volume, and so we can then cancel out our volumes, and we have a straightforward relationship then that P1 over T1 is P2 over T2. We know temperature is 273 plus 117 is 390 for the T2. T1 is our same 290 Kelvin, and so if we plug into this equation for pressure, P2 is P1 times T2 over T1, and so we end up with a pressure then of 6.7 kilopascals. So heating this mass up to 117 degrees C in this rigid container causes an increase in pressure from 5 kPa, which is what we started with, to 6.7 kilopascals. So we've got a slight increase in pressure as we increase the temperature. The next thing we'd like to do, the B part of the problem, is calculate the change in entropy, S2 minus S1, from this particular process as it's heated from 17 to 117 degrees C. Now this is what I was telling you about. You can use one of or either expression to solve for the change in entropy. You could calculate delta S is equal to C sub P ln T2 over T1 minus R ln P2 over P1, but that involves both the calculation of T2 over T1, P2 over P1, and the log term. Or you could use the other expression, that delta S is equal to C sub V ln T2 over T1 plus R ln V2 over V1. Well, the volume's constant, so if the volume's constant, V2 over V1 then goes to 0. The ln of 1 is 0, and so you can ignore that term here, and you only have to calculate or determine one expression to find the change in entropy. So the change in entropy then is equal to C sub V ln T2 over T1. C sub V again is found from page 52 for carbon dioxide, and it's 0.652 kilojoules per kilogram Kelvin. And so we've got temperature ratios 390 over 290, and so that turns out to be about 0.195 kilojoules per kilogram Kelvin, or the change in entropy for this particular process is about 0.20 kilojoules per kilogram Kelvin. And so this is what I was referring to earlier. Sometimes you may have a choice of equations to use. One equation may be obviously easier to use than the other one to save you some computational steps. You need to be looking for that in this exam because, as you know, you've got 120 problems to be working out in 240 minutes, and so you've got about 2 minutes per problem. And so if you can find any shortcuts on the exam to help you out with a little bit of time, you want to make sure you take advantage of those shortcuts. So these are two examples of the use of the ideal gas laws to calculate some relationship involving pressure, volume, temperature, or mass, and also a relationship using ideal gas laws calculating the change in entropy. So let's go now to, we'll be using some of the ideal gas laws later on in some of the other example problems, but I wanted to start with those just to give you some examples of what you would use in just a straightforward problem on the ideal gas laws. Okay, so let's now move into we're on page 6 of the notes. Let's move into the closed thermodynamic systems. Definition of a closed thermodynamic system is that no mass crosses the boundaries of the system. So in other words, mass is constant. You will very likely encounter two very common closed systems when you're working straight first law type problems. One is a piston cylinder arrangement where you have a gas contained within a piston, and the piston is either going to expand doing work or it will be compressed with external work done on it. The formulation of the first law, you're only involving, of course, work, heat transfer to or from the system, and equating that to the change in energy. The other type of common system that you'll run into in solving first law type problems will be systems that are constant volume as well as constant mass, and so this is just similar to the problem that we worked on the ideal gas law earlier, and that is we've got a rigid container that's a constant volume as well as constant mass, and so we'll be doing something to this, heating it, cooling it, or something of that nature, so that we will be using the equations for the first law to come up with the changes in internal energy or heat transfer or whatever. Now, the first law is formulated in our supplied reference as equal to Q minus W is equal to delta U. As you know, the first law deals with energy. If we define thermodynamics as equal to the study of energy and entropy, the first law deals, of course, with energy, and the second law deals with entropy. Now, sign conventions are important to note, and we need to point these out. They're very important because not all thermodynamics books use the same sign convention, and so it's extremely important to you to know which sign convention we're using in this particular section, because the problems and the solution to those problems are going to depend on using the same sign convention in the supplied reference as also that you use for the solution to the problems. Okay, sign convention, heat added to the system is positive. Heat added to the system is positive, so conversely, if you remove heat from the system, that's going to be negative, and work done by the system is positive. Work done by the system is positive. So if the system does work, if the system that we're looking at does work, then that's going to be positive in the equation, and if it does not, and if work is done on, let's say, our gas or our fluid here in this piston cylinder arrangement, then that's going to be negative. The other type of system that we want to talk about are open thermodynamic systems. These are discussed on page 44 in the reference manual. Open thermodynamic systems are also called control volumes. Those two names are synonymous with each other, and in the open thermodynamic system, both mass and energy cross the boundaries. Now, most all the time in the problems on the fundamentals of engineering exam, we're concerned with steady state conditions. There's a term over here that's in the rigorous formulation of the first law for control volumes that involves a change of energy term with respect to time, but we're going to pretty much deal with steady state conditions, and so the complete formulation of the first law says that all of the enthalpy, all of the kinetic energy, and all the potential energy changes for our system, plus the heat transfer into the system, minus the rate of work out of the system, is equal to 0. And so this is the general formulation of the first law, where we may have multiple inlets, 2 or 3 or 4 inlets, and we sum up all the mass coming into each of our individual inlets and multiply that by the enthalpy, kinetic energy, potential energy terms, and we subtract everything that's leaving our system. That's minus the mass exiting, however many exits we have, times the exit enthalpy, kinetic energy, and exit potential energy. And of course, the other part of the first law that's important to us is the conservation of mass equation, and that is all of the entering mass is equal to all of the leaving mass if there is no mass that's accumulated within the system. And so there are a number of different open system components that you're going to be responsible for. That is things like turbines, compressors, pumps, throttling devices, heat exchangers. These are all typical type of devices that we're going to look at for an open system, and we've got a bunch of example problems here that we'll go through for each of these types of systems. So let's first of all take a closed system example. Now, I've set up the next two example problems very different from the others that you're going to see, and I'm doing this for a very specific, to make a very specific point, and that is I try to set up this problem so that the statement is worded like the problems that you're going to be seeing on the exam. And so let's zoom in a little bit closer just on the example problem by itself, so without the solution on it, so that we will concentrate first of all on the problem. And let's zoom out maybe just a little bit more. Okay, so what we've got now is this is a closed system example. We've got a rigid pressure vessel that contains steam at 220 degrees C saturated vapor. Heat is removed from the system until the final temperature is 120 degrees C. The heat transfer for this process is most nearly. Now, this is the way the problems are worded, and there's almost every problem that has an example like this is worded is most nearly, and there are 4 multiple choice answers, and you've got to select the one that is most nearly correct. You notice here, and this is also common, you've got an A and a B. One is negative 2088, B is negative 1905, C is plus 1905, and D is 2088. And so in solving a problem like this, we'll get into kind of analysis of these answers here in a minute, but this is the way that a problem is typically set up. Now, I didn't go through and I set only 2 of them up under a multiple choice format, but I wanted you to make sure that this is the type of format that you're going to be seeing on the exam. Okay, so let's look at the solution now. And the solution is, first of all, we want to write the first law as Q minus W is equal to delta U, the formulation of the first law. Now, first thing I want you to look at is that the solution is in kilojoules per kilogram. So this means that the solution that's being requested is on a unit mass basis. So if we write the first law on a unit mass basis, we'll write small q minus small w is equal to delta U, and that way we've got it written on a unit mass basis. Now, there are a couple things here that I'd like to point out in this. The fact that you have the solution written in terms of kilojoules per kilogram, that means that you're not going to probably have to calculate a mass for the system. I did not give you a volume, but I could have given you a volume for the container, so therefore you could have calculated the mass in the system. Sometimes the problems contain more information that you really need to solve them, and so if you just go in and start solving everything that you can solve for in a problem without noticing what the form of the answer is, you might, as part of your solution, go ahead and calculate the mass. You don't want to do that. I didn't give you, in this case, the volume, so you can't do it. But many of the problems that you'll have will have more information in them than you really need to solve the problem. So on this one, you know you're going to have to work on a unit mass basis. Okay, so let's just go through a little bit of analysis here of how we solve this problem. First of all, you can draw a quick PV diagram to see where you are with the problem. You're starting out given that you are at 220 degrees C saturated vapor. So if you, on the PV diagram, if you just sketch out the process, then you know that you're going from state 1, which is at 220 degrees C saturated vapor, down to state 2. State 2 is at 120 degrees C. If any time that you're starting out under saturated vapor conditions and you're cooling off, lowering the temperature, you're going to have to drop into the mixture region, or the point 2 here that we're looking at is literally under the dome. So it's in the mixture region. Now, we also know that this is a rigid vessel. No work is done. There's no change in volume, so no work is done. So the first law is Q is equal to delta U is equal to U2 minus U1. So we can now go to the tables, the saturated table conditions, and I'm going to put this on here. This is, again, you don't have this in your notes, but it's page 48 in the reference manual. And so if we go to the reference manual to start with, we can pick out some properties on here, and we're starting out at a condition of 220 degrees C, saturated vapor condition. And so from the tables on page 48 and 220 degrees C, you come over and you read a value of 0.08619 for the specific volume and saturated vapor conditions, and you can come over here at UG and read a value of 2602.4 for the saturated vapor condition. So we're getting these numbers directly off of the table on page 48, the thermodynamic tables on page 48 for water, and this gives us the saturated vapor condition and the volumes as well as energies. Okay, so point 2 now lies in the mixture region, so it's under the dome. And so in order to find the U2, we've got to find the quality. Well, since this is a constant volume condition, constant specific volume condition, from page 43 we have the relationship that the specific volume at any point under the dome is equal to the quality X times VFG, which is the difference between the specific volume at saturated vapor conditions and the specific volume at the saturated liquid conditions, plus V sub F. So V is equal to X VFG plus VF. So the quality is the key term that you have to always find whenever you're in the mixture region in order to find the properties that exist at that particular point. So we know V2 is equal to V1. We just looked that up as 0.08619, and then if we go back to our table again, and we'll have to do some fancy thing to get back to where we were before, but we're now at this was our condition at 220 degrees C. Now we're going to drop down to 120 degrees C, and so at 120 degrees C we can look up the conditions for saturated volume. Here is 0.00106, and for the saturated vapor conditions we pick out 0.8919. Now while we're there, since we know we're going to have to be finding out information on the internal energies, you might as well pick off the internal energies. UF is 503.5, that's at 120 degrees, and 2025 is UFG, and UG is 2529.3. So we found that information then from the thermodynamic tables on page 48. All right, so if we go back now, we calculate the X. Knowing X, we have to calculate that from V is equal to VF over VFG. We have that information now that we've just pulled off the steam tables. I've repeated that information here that we've taken off the steam tables. So VF, VG, UF, UFG, and UG at state 2, and that state 2 of course is equal to 120 degrees C. Okay, so if we go through the calculations, calculate X, we find that X is 0.0956, and then from X we can then find the internal energy. Internal energy is X times UFG plus UF. We just looked up UFG at 120 degrees C and find out that that's 2025.8, so that's plugged in here. UF is 503.5, that's plugged in here, and we find that the internal energy at state 2 is 697 kilojoules per kilogram. So Q then is equal to delta U is U2 minus U1, so that's 697 minus 2602.4 is minus 1905 kilojoules per kilogram. Okay, now if we go back now to the original formulation of the problem, I'd like to go ahead and discuss that for just a minute. Set up the problem, and 2 of the answers were positive and 2 of the answers were negative. Now if we look at what's happening in the system, we've got a rigid pressure vessel originally at 220 degrees C. The heat is removed until the final temperature is 120 degrees C. Okay, heat is removed from the system, so therefore the heat transfer by our sign convention must be negative. All right, if you're just looking at this problem, you can immediately eliminate answers C and D, the 1905 and the 2088, simply because both of these answers are positive. So you know your answer is either going to be A or B to start with, and so you've eliminated 2 of the 4 answers right off the top because you know that the heat transfer has to be negative for this process. Now, this, if you sort of ran out of time and didn't, on a particular problem, and did not have time to go through the analysis to solve the problem, at least you'd be in a position to read over the problem and determine that you could eliminate 2 of your 4 answers to start with, because you know the answer has to be negative. And so even if you're in a guessing mode for the exam, a 50-50 guess is better than a 25% guess. So this problem is set up just like the problem on the exam. We know that heat transfers are removed from the system, therefore Q must be negative, and so those 2 answers, C and D, can be eliminated right off the top since they're positive. Okay, let's look at another example of a closed system problem. And this is a closed system problem that's going to involve sort of a piston cylinder arrangement, where you've got 2 kilograms of air contained at 800 kilopascals and temperature of 127 degrees C. We're expanding at constant pressure to a temperature of 227 degrees C. I'm making calculations easy, as you can see, because when we add 273 to those equations, they come out, and to those temperatures, they come out in nice round numbers, and so it's much easier to work with nice round numbers. Okay, we want to calculate the heat transfer during this process as well, and the heat transfer during this process is most nearly 4 different answers here. Notice that we've got the answers in kilojoules this time, and so we're going to have to multiply by the mass, but the mass is given in this case of 2 kilograms. And so we just got to make sure that we remember to multiply by the mass, otherwise we won't have the right system of units here. And again, A, B, C, D numbers are listed. What you'll also find on the exam is that the answers are set up either in ascending or descending numerical order. They're not random. So 72, 100, 144, 200 is the way they're listed here in ascending order, or in some cases they may be descending order, so A might be 200, B 144, C 100, and D 72. But they're not randomly mixed up. They're all going in order. Okay, so let's take a look at the solution to this one. This is a piston cylinder arrangement. We're starting out at initial conditions of 127 centigrade and 800 kilopascals, and expanding to a constant pressure of, at constant pressure to a temperature of 227 centigrade. Okay, and so if we start out with state 1, we've got 2 kilograms of air in here. Expansion takes place. That means work is being done by the system, so by our sign convention that's going to be positive work. If we sketch this out on a PV diagram, we're starting out with state 1, expanding to state 2. We know that we've got constant pressure involved here, and we also know that the area under the PV diagram is equal to work. So area is equal to integral of P delta V. P is constant, so we can pull it out, and this integral then says the work is just equal to P times the change in volume, or P times V2 minus V1. So if we write our first law, since work is going to be positive, Q is equal to delta U plus the work. We just put the work on the other side, and we can write this as equal to the mass times U2 minus U1 plus pressure times V2 minus V1. Now, if we take the if we look at the way this problem is set up, there are a couple of ways we can work it. One way, of course, is that we could just go ahead and evaluate U2, U1, V2, and V1 and plug into that and solve the problem directly, and that's an okay approach. But in a lot of these problems, a lot of the problems are set up on the exam so that there is an easier way to do it if you can find the easier way. There's sort of a shortcut. And one way of looking at this particular problem is to recognize that if you've got a constant pressure process here, and therefore you've got the pressure is P times V2 minus P times V1, you look back at these two terms here and you notice that the definition of enthalpy, H, is U plus PV. Enthalpy H is equal to U plus PV. So the short way to look at this problem is to recognize that since the enthalpy is defined as U plus PV, or total enthalpy capital H is equal to capital U plus P times V, if we combine the mass times the internal energy term MU2 plus PV2, that's H2. And M times U1 plus P times V1 is H1. And so this problem boils down to Q is equal to just the mass times the change in enthalpy. We also know that for ideal gases, and that's what we're working with here, H is equal to C sub P times T. So if you sort of recognize the shortcut on this problem, then you can combine the internal energy and pressure terms and recognize that specific heat is times temperature is the enthalpy. And so this problem that started out is involving calculations of changes in internal energy and changes in the work term boils down to a much simpler problem. So U2 plus PV2 is H2, U1 plus P1 or PV1 is equal to H1, and so that's H, and H is equal to C sub P times T. This is on page 43 in your reference manual. So Q then just boils down to the calculation of mass C sub P times delta T. C sub P, again from air for air, is on page 52 in the table, and so Q then is 2 kilograms times C sub P of 1 kilojoule per kilogram Kelvin times the change in temperature, 500 minus 400, and the answer is 200 kilojoules then when you multiply those out, so the key is D. Now, notice in this particular problem I went on ahead and added in absolute temperatures and converted that to 500 Kelvin and 400 Kelvin. I think you recognize that if you're taking the difference between temperatures, there's really not a need to convert to absolute units of Kelvin. But when you're working with ideal gas equations, it's just a good idea to automatically convert. That way you won't make a mistake if you have to solve for a temperature ratio, or if you have to solve for something in the ideal gas equation. You won't have forgotten, and you'll won't have plugged in degrees C instead of degrees K. Okay, so in this particular problem then the key is D, 200 kilojoules. And this problem, if you recognize that U plus PV is equal to H, comes into a very simple formulation of mass times specific heat times delta T, and it indeed is a 2-minute problem. It probably would not be a 2-minute problem if you had to go through and calculate, using the ideal gas laws, the two different volumes and then take the difference in those for the work term. Okay, now let's take a look at some open system or control volume problems. What we'll do first of all is we'll simplify the first law of the rate equation, and we'll simplify it by assuming that we are at steady state conditions as before, and we're only going to assume one inlet and one exit condition. Most of the problems that you're going to have, with the exception of heat exchangers, are going to involve a one inlet, one exit condition. You're likely going to have a turbine, you're likely going to have a pump, likely going to have a compressor or a nozzle or a diffuser, and so there's flow in the inlet, there's flow out the exit, and so you're only going to have one inlet and one exit condition. I do have one problem here as an example of a heat exchanger where there's going to be a couple of inlets and one exit, and so we'll show how to handle these problems if we do have more than one inlet and one exit condition. So our first law that we had written as an open system or control volume approach from page 44 simplifies to m dot 1, which is the entering mass, multiplied by the enthalpy of 1, V1 squared over 2 is the kinetic energy term, G times Z is the potential energy term, minus m dot 2 times H2 plus V2 squared over 2 plus G times Z. That's the exiting enthalpy, kinetic energy, and potential energy term plus Q dot in minus W dot out equals 0. So this is our basic equation for the first law, written as a rate equation for steady state conditions when we have only one inlet and one exit condition. Okay, now there are a couple different problems here that we'll work out involving first law examples for open systems. We'll start out first of all with a diffuser, and then secondly for a nozzle, and let's go over the assumptions that you're typically going to be making in these. If you have something obviously that's a horizontal device, such as a nozzle or a diffuser as we've drawn it here, the entering potential energy and the leaving potential energy are going to be the same. They're at the same elevation, so the change in potential energy is equal to 0. And all of these things, you have to analyze each one individually and determine what terms you can throw out. If you had to solve this equation on every one, these would be more than 4-minute problems, so you wouldn't be able to solve, you really wouldn't be able to solve problems like this on this exam. In this particular case, there's no work being done for either a nozzle or a diffuser, and so that term goes out, potential energy terms go out. Typically, you also assume that there's no heat transfer, so a typical assumption on something like this is that the change of potential energy is 0, there's no work being done, heat transfer is equal to 0. And of course, in the case of a diffuser, your interest is in slowing down the velocity of the fluid or increasing the pressure, whichever way you want to say it. And so what happens in the case of diffuser is that with an entering velocity and entering pressure, V1 and P1, V2 is less than V1 and P2 is greater than P1. So these are the equations that you're dealing with, and so the terms that are generally significant are the kinetic energy terms and the enthalpy terms. For a nozzle, you've got just the opposite case. In the case of the nozzle, you've got V2 greater than V1, you're speeding up the fluid, and the pressure P2 is less than P1. So let's take an example now where we're going through and solving for the conditions for a nozzle. And we're going to start out here in this example. This is example 5. We're on page 11. We've got steam flowing through a nozzle that's operating under steady state conditions. The nozzle pressure fairly high, 0.4 of a megapascal, an initial temperature of 300 degrees C. And at the nozzle exit, we're expanding down to a fairly low pressure. P2 is 0.5 megapascal, and the exit velocity V2 is 300 meters per second. Okay, so what we're after here, we're told in the problem to ignore the entering kinetic energy. The other usual assumption is that there is no work done, the heat transfer is 0, the change in potential energy is 0, and so we're left with an expression here where we're going to throw out all of the terms except the enthalpies and the exit kinetic energy. We're told to ignore the entering kinetic energy as well. Okay, so let's zoom in a little bit more on the this little diagram here so that we can see exactly where we are. This is a TV diagram now. We've got 0.4 of a megapascal up to 300 degrees C, and so our entering condition at state 1 is in the superheated region, and we're expanding down to a pressure of 0.05 megapascals, and so we're going to be expanding around to a little bit lower temperature as well as a significantly lower pressure. Now if we go to the steam tables to find the initial conditions, and again these are steam tables that are going to be difficult for you to read, except that what we'll attempt to do is zoom in exactly on where we are, and that is we are at 0.4 of a megapascal and 300 degrees C. So looking at 400 megapascal, excuse me, 0.4 of a megapascal and 300 C, we can go in and find the enthalpy at this particular condition at 3066.8. And so that is our enthalpy at state 1, entering the system, entering our nozzle. And so our expansion then is down, and we want to find the final enthalpy. Okay, so we can go back to our a little graph here. We know that we are at 0.4 of a megapascal. We just calculated the enthalpy here. Let's go to our first law equation. We'll have to make it a little bit smaller here. First law equation, then, we're throwing out entering kinetic energy. Now this term would not necessarily be thrown out in all cases, but we're given that the entering kinetic energy is small compared to the leaving, so therefore we can neglect that. We can neglect the potential energy term. We can neglect potential energy term leaving, and we are told that there's no heat transfer, and we know there's no work done. And so our problem really reduces down to enthalpy of 1 minus the enthalpy of 2 minus the kinetic energy, or the V2 squared over 2 term, equals 0. From that, we can then determine what the final enthalpy is. Okay, so we just looked up on page 49 from the steam tables at 0.4 of a megapascal and 300 degrees C, we find enthalpy of 1 is 3066.8 kilojoules per kilogram. So we plug this back into our equation, and the enthalpy of 2 is 3066.8 minus 300 squared over 2 is the kinetic energy term. And I've filled in all the units here for you. That's meters squared per second squared, and then we've got to convert that into the definition of a Newton, which is a kilogram meter per second squared. And then we've got to fill in what the definition of a kilojoule is, and a kilojoule is a Newton meter, and then you've got 1,000 Newton meters per kilojoule. So when you plug in all those units, cancel them out, making sure your units are compatible. And this is real important to remember this little, you've got your answer in kilojoules, so it's real important to remember this 10 to the third Newton meter per kilojoule conversion. Otherwise you get huge answers that are in error by a factor of 1,000. So if you're not familiar with the conversion here in kinetic energy, you ought to work out some of them just to make sure that you've got the right units. Meter squared per second squared does indeed convert to kilojoules per kilogram if you run through the normal conversion here, and make sure you include the 1,000 Newton meters per kilojoule. Okay, so the kinetic energy term then turns out to be about 45, as you might expect, not really highly significant compared to the initial enthalpy. So when you take the difference here, H2 then turns out to be 3021.8 kilojoules per kilogram. And so this is an example of using the steam tables to find the information that you need. We could have had a problem where it involved ideal gases as well, and worked out a similar sort of thing, except we've been using the ideal gas equations to find enthalpy, which is from our last problem, C sub P times T. But this is an example of the use of a first law analysis for control volume, in particular with a nozzle, and using the steam tables to come up with the values of the properties. Okay, now let's take the same problem as an example problem, and what we'd like to do now is do a little bit more work with the steam tables to come up with the answer to this one. So this is going to be kind of an exercise in the steam tables. We've got the same problems we had before, except now we'd like to find out the temperature of the steam leaving the nozzle. The temperature of the steam leaving the nozzle. That's something that you have to get out of the steam tables. We know that the temperature is going to drop a little bit just as the enthalpy drops. The temperature is going to drop a little bit as the steam leaves the nozzle. We found the enthalpy, so we can use the steam tables now to go back and find out what the temperature is of that steam leaving the nozzle. So again, we've got the same exact setup as before. State 1 was at 0.4 megapascals and 300 centigrade. State 2 we've now found is an enthalpy of whatever we had before, and let me look back, 3021.8 kilojoules per kilogram. So we know what state 2 is, and so what we'd like to do is use the steam tables. This is a table lookup and really an interpolation problem. We already know what H2 is, 3021.8. So now what we want to do is go to page 49 of the reference manual, and let me stick that page back up here again and find out exactly where we are on it. Okay, we are at 0.05 megapascals, and then we've got an enthalpy that we want to find of 3021.8. Okay, so what we're trying to do is find out where we are on the enthalpy curve, and we've got an enthalpy of 3021.8, so we are between a temperature of 300 degrees and a temperature of 250, and we'd expect that's where we'd start out, because our temperature doesn't drop too much as the flow goes through a nozzle. But this is an interpolation problem. We have an enthalpy of 3021.8, and the temperature is going to lie between 250 degrees centigrade and 300 degrees centigrade, and so in order to find the temperature, we've got to interpolate between those two values that are on the table. Okay, so if we now go back to the interpolation here, okay, we see that the temperature of state 2 is between 250, which has an enthalpy of 2976.0, and 300, which has an enthalpy of 3075.6, and we are at 3021.8. So you linearly interpolate between the two. This value of 3021.8 is almost exactly halfway between 250 and 300, and so our temperature of the steam exiting the nozzle then is 273 degrees centigrade. And so this would be a way of going through. It involves a little interpolation of the tables. You could have a problem like this. What would likely happen if you had a problem like this is you might be given that the enthalpy is, you might not have to actually calculate the enthalpy. You may be given what the enthalpy is and then go to the tables as a lookup and determine what the temperature might be. All right, so let's now take an example of another open system device, and this time we want to use a compressor and solve solve a problem with a compressor. And what we have in this particular case, we're going to be using now ideal gases. So example number 7, page 13, we've got 1 kilogram per second of nitrogen gas entering a compressor. Compressor is operating under steady state conditions. The entering conditions are P1 equal to 1 times 10 to the 5th pascals. This is not kilopascals. Now this is pascals. That is roughly atmospheric conditions. So one bar is roughly equivalent to, or 1 atmosphere pressure is equivalent to about 10 to the 5th pascals. The temperature is 290 degrees Kelvin, so this is again sort of an atmospheric condition where you've got nitrogen entering under no pressure and very little temperature, and you're exiting at P2 of 7 times 10 to the 5th pascals, and so you've got a compression ratio here of about 7 to 1 on the nitrogen. The leaving temperature conditions is 450 degrees Kelvin, and in this particular case, although one of the assumptions that's normally made for compressors is that there are no heat losses, in this particular case we do have heat losses that occur at the rate of 200 kilojoules per minute to the surroundings. We're also told in this particular problem to neglect potential and kinetic energy changes, assume ideal gases, and we want to calculate the work done in kilowatts. Okay, so let's set up the problem. We've got compressor having nitrogen gas in at about 1 kilogram per second, entering pressure and temperature conditions, roughly atmospheric conditions. We've got a work input device, of course, for a compressor. You have to put work in to make the compressor operate. We have heat losses in the system, 200 kilojoules per minute. It is losses, so therefore the Q term is negative when we plug it into our equation. And then the exit conditions here, pressure and temperature, are given as 7 times 10 to the 5th pascals and 450 degrees Kelvin. All right, so if we go down to our first law as a rate equation, we are neglecting the kinetic energy term, we're neglecting the potential energy term, so that leaves us with mass times enthalpy entering minus mass times enthalpy leaving, plus heat transfer into the system. In this particular case, we've got Q out of the system, so we know when we plug this in it's going to be negative, minus the work out for the system. And in this particular case, we know that we've got a work input, so we know that the work out term is also going to be negative. Nitrogen, again, goes to page 52. Look up the properties here for the nitrogen, and we'll see that the CP is 1.04 kilojoules per kilogram Kelvin. And so now the work of the compressor, which is what we're solving for, is going to be equal to the flow rate, m dot, of 1 kilogram per second times specific heat times the delta T term. This gives you the term for the change in enthalpies. You've got kilojoules per minute for the heat loss, so you've got to convert that into seconds because we want this in kilojoules or joules per second, and so that's dividing by 60. And so the work of the compressor then is equal to 301.6 minus 468 minus 3.33. The 3.33 is the heat loss term. It's small compared to the other terms, and that's one of the reasons why normally you could assume that the heat losses are fairly small from something like this. So the work of the compressor then comes out to be about minus 170 kilowatts. And so that is how much work you would have to put into the compressor. That's the size of motor that you would have to have in order to accomplish this compression for a kilogram per second of nitrogen, which is a pretty heavy load and quite a lot of compression that would be required to do that. Now, a couple things that I'd like to remind you of on the expression here that we just found. That is, a watt is 1 joule per second, so therefore 1 kilowatt is 1 kilojoule per second. You've got to make sure that the units are always compatible, and some of you may be used to working in SI system and metric system and be very familiar with that. Others may not be, and so you need to really practice and get familiar with the SI system. We already pointed this out when we were going through the problem solution, but Q dot N is negative because it's heat lost by our sign convention, and the work of the compressor is negative because it's a work input into the system. And so just a couple of reminders here dealing with unit conversions and also making sure that you're familiar with the sign convention. Some of you may have used a textbook when you went through your programs and studied thermo that used a different sign convention. So just make sure that you have a compatible system whenever when you go through and solve the problems. Okay, the next example that we're going to take a look at here is a mixing device. And so what we want to do in that particular case is take a look at a small mixing tank where we want to increase the energy of the steam leaving a mixing tank. And so the way this is set up, it's a mixing device. Now this is one of them I was talking about earlier that had more than one inlet condition. And so in this particular case, we've got a mixing tank set up with 2 inlets. We've got steam coming in one side. We've got subcooled liquid water coming in at another port, and leaving we've got steam, we've got saturated liquid leaving. And so what this is we've got steam that's mixed with a liquid. In this case it's going to be subcooled liquid, and we'll remind you what the definition of subcooling is in a minute. And we want to, the whole point of this is to raise the liquid temperature leaving to saturated conditions. In a power plant, for instance, You have a higher efficiency in the boiler, for instance, if the water entering the boiler is at a higher temperature. And so this is a common process that's used in a power plant to raise the energy of the water entering the boiler. And so you do this generally by pulling steam out during the process and mixing this generally low pressure, low energy steam with liquid water in order to raise the energy level of the water entering the boiler. Okay, so this is our setup then. We have water, liquid water that's subcooled, and subcool means that it actually exists at a temperature below its normal saturation temperature corresponding to the pressure. So we've got 1 megapascal pressure, the temperature is 40 degrees C, and we've got 100 kilograms per second of liquid water that's entering the mixing tank. We have steam entering at 1 megapascal pressure as well, saturated vapor. We don't know how much is entering. That's what we're after. We want to find out how much steam we have to mix with this water in order to raise the water up to saturated liquid conditions. So first of all, we want to apply our conservation of mass equations, and we know that if liquid water is entering here and we've got steam entering here, all of it's going to flow out. So m dot 3, the amount of mass that flows out of the tank, is going to be the sum of m dot 1 plus m dot 2. So this is our conservation of mass equation that we get out of the first law. We're going to assume that we've got no losses throughout our mixing tank, that it's well insulated so we don't have heat transfer losses. There's no work being done. We're going to assume that there's not going to be any significant change in kinetic energy or potential energy. And so we've got a very simple expression that we have to solve then for the first law for this particular problem, and that is m dot 1, which we know is 100 kilograms per second, times the enthalpy at 1, plus m dot 2 times the enthalpy of 2 is equal to m dot 3 times the enthalpy of 3. So this is our first law conservation equation that we need to solve in order to come up with the amount of steam that's required to accomplish this particular heating. Okay, so now we've got to go to the steam tables because we've got to find out the amount of energy or enthalpy that exists at all of these conditions. And so what I'd like to do is go back now to page 48 in your reference manual. And at page 48 in the reference manual, we're going to see if we can zoom in on this just a little bit. We're after the enthalpy of the fluid entering conditions. Okay, now to just refresh yourself for just a moment, if you have a liquid that is in the subcooled state, if it's not under very high pressure conditions, then you determine the enthalpy of a subcooled liquid by looking at the temperature of the liquid. And in this particular case, we have 40 degrees C, and so what we will do is come down to 40 degrees C in the table and go over to the enthalpy at 40 degrees C, which is 167.57, and so the state 1 would be found at 40 degrees C, saturated liquid condition. Now if you had a highly compressed liquid, then you would end up with a little bit higher enthalpy, and you'd have to go through and determine from compressed liquid tables or some other equation what the increased enthalpy is. But in this particular case, we're trying to keep, for the reference manual, trying to avoid a lot of unnecessary tables. And so what you have in this one is that there are no compressed liquid tables, and so we'll simply be using the enthalpies coming off of the temperatures corresponding to the table coming off to the temperature. So 40 degrees C, you've got 167.57 as the enthalpy. Okay, we also can find state 2, and state 2 we know we've got saturated vapor at 100 at 1 megapascal. And so now let's go down to our tables till we come to a pressure of 1 megapascal. And if you notice on your tables, this is a temperature table, not a pressure table. Some of the thermodynamic tables will also provide temperature data as well as pressure data. But in our particular case here, this is set up so that it's in even increments of temperature. So sometimes you won't be lucky enough to find an exact equivalent on pressure, so you'll have to do some interpolation. But in this particular point, if we come down here to 1 megapascal, we have a tabular value that's 1.0021 megapascals, and so that's plenty close enough for these most nearly correct sort of answers that you get on the FE exam. 1.002 will provide you an enthalpy value that'll be close enough to what you can work on the exam. So you come over to the saturation conditions, and you see that you've got a value of 2778.2 for the enthalpy at 1.0021 megapascals, which is close enough to 1 megapascal for us to solve the problem. And then we also know that it leaves the heat exchanger at state 3 as a saturated liquid condition, so we also can look up on the same 1.002 and find out that the saturated enthalpy is 763.22. And so this gives us the information we would need on the problem to plug it in and solve for the missing terms. Okay, so I've got this summarized on this particular page. We're on page 15 now. So I've got it summarized on this particular page, and we see that state 1 is 167.57, found at 40 degrees C, saturated liquid conditions. State 2, saturated vapor 1 megapascal. We've actually looked at the conditions of 1.002, but that's close enough. Find out enthalpy of 2778.2 kilojoules per kilogram, and then 763.22 kilojoules per kilogram saturated liquid at 1 megapascal. Okay, conservation of mass equation then. We know that m.1 plus m.2 is equal to m.3, and we know that m.1 H1 plus m.2 H2 is equal to m.3 H3. So m.1 is 100 kilograms per second. Multiplied that by the enthalpy of 1, which is 167.57. m.2 is unknown. That's really what we're after, because that's the mass of the steam. The mass of the steam enters with an enthalpy of 2778.2, and then that's equal to the leaving mass, which is our 100 entering M1, plus M2, which is m.2, which is unknown. But we know that we want to raise that up to an energy level or enthalpy level of 763.22. So if you solve this equation, you can go through the algebra. I hope I've done the algebra right, but you can check me out as you verify these numbers. But you get from this m.2 is equal to 29.6 kilograms per second. So for this particular problem then, it takes 29.6 kilograms per second of steam to mix with the 100 kilograms per second of water to raise the overall energy of the leaving water up to an enthalpy level of 763.22. And so this would enable you to use the second law, the first law equation, for a rate equation, and with 2 inlets, 1 exit. So that's just an example of the type of problems that you might encounter in a heat exchanger. So just to kind of summarize here, we've talked about compressors, we've talked about nozzles, we've talked about heat exchangers. A little later on, when we get into cycles, which is our next topic, we're going to get into looking at turbines and expansion devices. And so we're going to probably work example problems of virtually every type that you're going to encounter on the FE exam, either through the ones we've already worked, just dealing with a single component, or by working in a cycle. So the next thing we're going to go ahead and start on are cycles. And These are the 5 cycles that I said in the beginning. We're on page 16 in the notes. 5 cycles that you need to be familiar with. First is our old friend, the Carnot cycle, which is probably the most famous cycle in all of thermodynamics. The reversed Carnot cycle, which is a refrigeration cycle. The Otto cycle, which is the cycle for the gasoline engine. And Rankine cycle, which is the power cycle. And then the reverse Rankine cycle, which is refrigeration. Now, I didn't copy this particular page out, but if you want to look at page 47 in your reference manual, you'll see all of these cycles that I've just talked about here. You'll see all these cycles that are listed, and the cycle diagrams for them are included here on this page for the Otto, Carnot, Rankine cycle, refrigeration cycle, and reverse Carnot. So all of these are in there. I didn't duplicate this page, but you'll have it in front of you. So page 47 in your reference manual, you'll have cycle diagrams for all these cycles. And of course you'll have this to refer to also whenever you run into a cycle problem. So it tells you what the TS or the PV diagrams look like for these. Now, when you run into these questions on the exam, the morning or the AM questions will generally be single process questions, and that is you might be asked to find the work or the heat input for a single part of a Carnot cycle that's going from state 2 to state 3 or something like this, or for an Otto cycle. The afternoon questions are generally going to involve the analysis of a complete cycle, and so they're a little longer problems, and quite often in the afternoon the problems involve a single stem, that is a single question, and then multiple answer questions that are asked for maybe a complete cycle analysis. So let's go over a few definitions now for a power cycle, just to refresh yourselves on the efficiencies. The efficiency of a power cycle is the net work divided by the heat supplied. Net work divided by heat supplied, or W net over QH. And in most of the power cycles, some of the power cycles, you're only going to have one heat input. Others, you're going to have more than one heat input. But it's the heat supplied in the cycle divided into the net work out of the cycle. Now, for our old friend, the Carnot cycle, which also applies to any reversible cycles as long as they are fully reversible. The efficiency of the Carnot cycle, which is generally said is the highest efficiency that you can encounter, or as it would be for any reversible engine. QH minus QL over QH. The net work is defined as QH minus QL. Heat input's QH. And if we're talking about the Carnot cycle, we can relate the heat input to the absolute temperatures. So QH minus QL becomes TH minus TL, QH becomes TH, and so for the Carnot cycle breaks down into the efficiency of the Carnot cycle is 1 minus TL over TH. Again, reminder, temperatures have to be in absolute values. And so these are some of the things for power cycles, either for a Carnot cycle or for the Rankine cycle. And now we'd like to take a look at a reversed Carnot cycle for the refrigeration, and again talk about the terms here, and we're now on page 17. For reverse Carnot cycle, which is the refrigeration cycle, it doesn't make sense to talk so much about efficiencies, because for a refrigeration cycle you're not interested in how efficient the cycle works. You're really interested in heating or cooling, depending on what your cycle is with a refrigeration or a heat pump. So instead of talking about efficiencies as you do in a power cycle, you talk about terms like coefficient of performance, or COP. And the COP is defined as the desired effect, whatever you're trying to accomplish, and that is either heating or cooling, divided by whatever it costs you to accomplish that desired effect. And so the way I like to look at it is if you're in the cooling mode, your desired effect is how much heat you can remove from your house or your room, and then, or from your refrigerator. If you're in a heating mode, then you're interested in the amount of heating that you can get, or how much heat can be supplied, divided by the energy that it costs you to do that. You'd like to do that as efficiently as possible, and so the terms that are used are coefficient of performance to give you the desired effect, that is either heating or cooling, divided by the energy that costs. So if we go back now and define this in terms of the equation, the COP for cooling in the ideal Carnot cycle, you're interested in the cooling effect, so you're interested in the low temperature of the heat removal, QL, over QH minus QL. And then since we're talking about a Carnot cycle, we're talking about the ideal cycle, we can also say that that corresponds to TL over TH minus TL. So you can find the theoretical efficiency of a Carnot cycle for cooling just by dividing the low temperature by the difference between the high temperature and low temperature. And for heating, you're interested in the heat transfer on the high side, or the heat removal, QH over QH minus QL. This, of course, is the work term, so the energy that costs you is the work. And so this then is TH over TH minus TL. Again, TH minus TL is the work term, and TH is the heating. So you have two terms when you're talking about refrigeration cycles that are important to you. One is the coefficient of performance for cooling, defined as TL over TH minus TL, and for heating it is TH over TH minus TL if you're talking about the Carnot cycle. Okay, so let's now take an example of the thermal efficiency of a Carnot engine operating between the temperatures of 800 Kelvin and 300 Kelvin. So we're talking about a Carnot engine here, so now we're talking about a power device, and the solution that I like to sketch these things out so that we talk about having a thermal energy reservoir. That's nothing more than heat source, a high temperature heat source. In an engine, it would correspond to a combustion chamber. In an aircraft, it would correspond to a combustion chamber. In a power cycle that we're talking about here, is just a high temperature heat source. And so a TER is what I've labeled here as a thermal energy reservoir, and it's operating on the high side at 800 Kelvin. The other thermal energy reservoir is located is at a temperature of 300 Kelvin, and that's essentially the atmosphere. So that's just the rejection at 27 degrees C into the atmosphere. So what we're after, we've got a Carnot engine operating between these cycles, and we want to calculate the thermal efficiency. Well, if you get a Carnot cycle problem, it's going to be a very straightforward problem. So all you have to do is remember that you're using absolute temperatures here when you plug into the equations. I've made it easy for you by giving the problems in terms of absolute temperatures, but it could have been given in terms of degrees C or degrees F, and you'd have to do the conversions to get it into the absolute terms. Okay. Thermal efficiency of a Carnot cycle is just a function of the high temperature thermal energy reservoir and the low temperature thermal energy reservoir. So Carnot efficiency is TH minus TL over TH, which is 800 minus 300 over 800, and so the Carnot efficiency is 0.625. So if you have Carnot efficiency problems, and it becomes a fairly simple matter then to determine what the efficiencies are. Now, of course, I should also mention that you can have lots of variations of this problem. So let me just talk about those variations. I did use this as an example problem, but you could have any combinations. You could have the high temperature given at 800 Kelvin. You could have the efficiency, and then you could be asked to find what the temperature of the low reservoir is, the thermal energy reservoir. Or you could be asked to just determine what the work output is, which would be the difference between the 800 and 300. This could be given in Qs, and you could be given 800 kilojoules supplied. You could be given an efficiency here of the engine, and then asked find out how much heat is rejected into the low temperature reservoir. So there are all sorts of combinations that you can get with this. But all the Carnot engine problems all involve calculation of absolute temperatures, RQs and Ls, and efficiencies. And so you might get different combinations of problems, but they're all going to work pretty much the same way. Let's now take another example. Example number 10. We've got a reverse Carnot cycle. A reverse Carnot cycle is a refrigeration cycle. And this particular case, we've got the Carnot cycle that operates between 50 degrees C and 0 degrees C. And we want to calculate the coefficient of performance for cooling, which I've called COP sub C, and the coefficient of performance for heating, which are called COP sub HP for a heat pump. Okay? And don't forget to convert to absolute temperatures. I'm going to preach that to you a lot because it's real easy to make mistakes on these cycles if you don't convert to absolute temperatures. Okay, in this particular case, we've got a thermal energy reservoir, TER, at 50 degrees C, which is equal to 323 Kelvin. And we've got a low temperature reservoir at 0 degrees C, or 273 Kelvin. And so this is our little sketch here. We're going to have work input. As a consequence of the second law, you can't transfer energy from a low temperature source to a high temperature source unless you do work on it. And so that's the whole principle of a refrigerator, is to be able to transfer energy from a low temperature to a high temperature with work being done on the system. Okay, COP for cooling is QL over QH minus QL, which for a Carnot cycle is TL over TH minus TL. And so COPs then for cooling, 273 is our low temperature reservoir divided by the difference, 323 minus 273. COP for cooling is 5.5. Again, you would not have to converted these to absolute temperatures because the difference between Kelvin and centigrade is, when you're talking about temperature difference, of course, are exactly the same. However, if you didn't convert the 273 to absolute temperatures, you'd end up with a 0 on top, and you get a COP of 0, of course, and that would be the wrong answer. So you get a COP for cooling of 5.5. For heating, you get your COP for a heat pump. This is operating as a heat pump where you're interested in providing heat into the system. And so this is QH over QH minus QL. QH minus QL is the work, or the energy that costs, and this can be converted into absolute temperatures by TH over TH minus TL. And so for heating, you're interested in the high temperature reservoir, it's 323, and so you got 323 minus 273, so you get a COP of 6.5. Now, notice that in the case of efficiencies, you're only interested, and you're only getting answers that are between 0 and 1. The Carnot efficiency, of course, for a heat engine or for a power plant is the maximum efficiency that you can achieve, and in real life you're not going to get that much. But coefficient of performances here are numbers that are greater than 1, and so that's good. You would like for the COP to be as high as possible, because the COP of high as possible means that you are delivering heating or cooling at a high efficiency. And so what you'd like to have would be coefficient of performances that are in the neighborhood of 3 or 4 or 5 or something like this, to ensure that you're delivering the heating or cooling as efficiently as possible. The COP is also related to things like the SEER, the SEER that you see for air conditioners, but those don't have anything to do with the fundamentals of engineering exam, so we won't go over those. Okay, next thing we're going to do here is to take a look at a Rankine cycle, and it's a power plant cycle. This is example number 11. We're on page 19. We got a simple power plant, operates on a cycle that's shown here on the TS diagram. We got pressures and temperatures as indicated around the cycle. And so the very simple cycle here that we're going to look at for the power plant involves pumping from point 1 to point 2. So 1 to 2 is where the pump is located. 2 to 3 is the heat added in the boiler. So you're taking it from the outlet of the pump, taking it into the boiler, heating it up, changing it from liquid water through the mixture region, saturation region, into superheated steam. You're expanding it through the turbine from 3 to 4. That's where the useful work comes out of the system. And then you're condensing that steam in a condenser that goes from 4 back to 1 again. Now what we did on that little problem where we did the mixing problem, we essentially got the fluid from, we put in an intermediate stage between the condenser and the pump where we heated the liquid water up to a little bit higher condition in order to have a more efficient, higher energy value of the liquid entering the boiler. But in this particular case, we're not going to assume anything except 4 very simple components: boiler, a condenser, a pump, and a turbine. So this is our simple power plant cycle. These are the states that are given. State 1, which is the condition entering the pump, 70 kilopascal saturated liquid. State 2, we're given the pressure of 10 megapascals. State 3, we're given the pressure, temperature, entropy, and enthalpy conditions. And State 4, we're given the pressure conditions here and entropy conditions. And we're given that this, in our very simple cycle, highly idealized, we're given that the turbine work from 3 down to 4 is reversible, so that the entropy is constant from State 3 to State 4. So this is an isentropic expansion through the turbine. Now, one of the things that it's important to point out to you is that when you've got properties such that if you look back in the tables in your reference manual, you wouldn't find these properties in there because our reference manual doesn't provide pressures as high as 10 megapascals. And so that doesn't limit you, however, in solving problems of this type, because all of this that we're talking about here in this problem would be considered to be the stem of the problem. And so you might be given a figure, and you might be given properties all around the cycle at different points. And so even though that some of these properties are not in the back of the table, they've been taken from other tables, and so these would just be given to you. So you'll see a lot of problems, particularly in the PM, the afternoon section, where you'll have properties that are just given to you that are part of the stem of the problem. Okay, this is one of those multi-part problems. We want to analyze everything that we can around this cycle. We want to find the turbine work, the pump work, the heat supplied in the boiler, the overall cycle efficiency, the megawatt output of the turbine if it's got 100 kilograms per second of steam flow through it, and then we're going to get into isentropic efficiency of the turbine for a situation where the turbine is not expanding isentropically as we have shown here, but rather it expands to a different location. So this is one example problem, but it involves 6 different parts. Now, if you have something like this on the FE exam, what's likely to happen is that you might be given a cycle and you may be asked to determine 1 or 2 or 3 of these different values, and you would not, very likely would not ever have a problem where you'd have to calculate all 6 of them. Another thing that you try to do in given problems is you try to give problems where the answers to A are not given, or don't depend on your answers to, let's say, D. But in this case, obviously, you'd have to calculate the turbine work and the pump work in order to find the cycle efficiency, and you'd also have to find the heat supply in the boiler. Many times in problems like this, you'll be given a turbine work, or you'll be given a pump work, and then asked to find the cycle efficiency, and just trying to test your ability to understand what cycle efficiency is without having to have the answer to D, for instance, that is dependent on calculated answers in A and B. Not all the time, though, does that work, because there are some problems where you end up, you have to use answers that you get in a previous problem in order to solve a given problem. And so in those cases, you just got to make sure that you get the right answers. Okay, so let's go through this on solutions, and we're going to go through this and assume that this is sort of one problem at a time, and we're going to go through and analyze each one of them in order to come up with the work. So turbine work, the work of the turbine. This is again a device that we talked about. It's a device that has a control volume approach, typically one inlet and one exit on these simple problems for simple power plants, and we ignore kinetic energy, we ignore potential energy, we ignore any heat losses, and everything's well insulated. And so in the simple analysis of the turbine, the work then turns out to be just equal to H3 minus H4. Okay, point 4 lies in the mixture region, so we've got to find the quality X in order to find the enthalpy at 4. Now, in this particular case though, if it is an isentropic expansion, that is constant entropy, we know the entropy at 3, and so it's got to be the same as the entropy at 4. And so it works out very similar to one of the example problems that we used earlier. You find the quality X, and then after you find the quality X, you can find the enthalpy H. In this particular case, since we've already gone through and looked at tables to locate the values, we're not going to go, we won't show the tables on here this time. I've looked them up, and assuming I haven't made a mistake in looking these things up off the tables, I'll just give you what I got off the tables for the enthalpies and the entropies at the various locations. So page 48 on the tables, at the pressure value of 70.14 kilopascals, and we look up and find SF, which is the entropy at the saturated conditions, 1.1925, SFG 6.2866, SG, which is the entropy at this point here corresponding to the saturated vapor condition, is 7.4791. Similarly, HF is 376.92, HG is 2660.1, and so HFG, which is HG minus HF, is 2283.2. So we can then solve for the entropy. S is equal to X, SFG plus SF, and when we plug in the numbers up here, our entropy is 6.6622. That's found from state 3. It's the same as it is at state 4 if we have an ideal expansion. And so we plug in these numbers here, and we get out of the tables, and we come up with an entropy, with a quality of 0.87. So the quality X is 0.87. It means it's fairly close to the saturated vapor line, mostly vapor, but there is some liquid that's present in the process. Okay, so we could use H4 then is equal to X times HFG plus HF, or the enthalpy at state 4 is found from the quality at state 4, which we just determined, HFG and HF, and so we plug in the numbers, plug in the expression for enthalpy. We get H4 is 0.87 times 2283.2, which is the value here, plus HF, which is 376.92, and we have H4 then is equal to 2363.4. So that gives us the enthalpy then at state 4, and that's what we need in order to find the turbine work, H3 minus H4. And so plugging that in, work of the turbine then, H3 minus H4, that's 3425.1, which was the enthalpy at 0.3, minus 2363.4 that we just calculated, and that gives us the turbine work then as 1061.8 kilojoules per kilogram. Turbine work is expressed in kilojoules per kilogram because we haven't at this point been given a value for the flow rate in kilograms per second, but if we were given kilograms per second, as we're going to have in a latter part of the problem, then we'll be able to calculate what the actual megawatt output of the turbine is. Okay, the next thing we're asked to find is pump work, and pump work is in kilojoules per kilogram, and if you we'll make the assumption here that water is incompressible, and so therefore the volume remains constant for water as it's being pumped, and so the expression for pump work is minus V times P2 minus P1. This is on page 44 in the reference manual, And so what we're after then, if we go back up to our condition here, entering the pump, and we're pumping from point 1 to point 2 from our original diagram. So we look at the specific volume of water, 0.001036 cubic meters per kilogram. Find from the tables on page 48 at the pressure of 70.14 kilopascals, V sub F. And so the pump work then is minus V, which is 0.001036, times delta P. And we're pumping it from 70 kilopascals up to 10 megapascals. And so I've just converted this, I've kept it both in kilopascals, so we're 10 times 10 cubed kilopascals minus 70 kilopascals, and turns out to be minus 10.3 kilojoules per kilogram. Again, it is negative because it's work input into our system. We're having to do work on the water in order to pump it up to the higher pressure condition. So the work of the pump then is minus 10.3 kilojoules per kilogram. But if you look back at the turbine work is 1061.8. So the pump work actually represents only about 1%, about a 1% penalty when we're pumping the liquid up to the higher pressure condition. Okay, so we've now calculated the work of the turbine in kilojoules per kilogram. We've calculated the pump work, which is minus V times delta P. And so now we'll go to determining what the heat supplied is for the boiler. And again, we're using kilojoules per kilogram, so we're just looking at the energy that must be supplied per kilogram of water or steam flowing through the system. Q in the boiler, if we go back to our, let's go all the way back to our original cycle here just to make sure that we are on the same page. And let's zoom in just a little bit on this one. And this will give us, if we go back to our original cycle, then we know that process from 2 up to 3 is involved with the heat transfer in the boiler. So the water enters the boiler under a condition of 10 megapascals and is then heated as it goes through to saturated conditions, saturated liquid conditions, and it goes through a vaporization process, and then it becomes superheated as you move out into the superheat region. So the heat added in the boiler is the heat that's added from state 2 to state 3. Okay, so now if we, this is a matter of finding Q sub B as H3 minus H2. H3 we've already found is 3225.1, it's the enthalpy at 0.3. Now we've got to find H2. Now, you would not introduce a large error in your problem if you said, okay, the pump work is really negligible and the enthalpy at 2 was equal to the enthalpy at 1. That would not introduce a large error. However, it would probably turn out to be a mistake that you wouldn't want to make. Even though the pump work is small, the enthalpy at state 2 is approximately equal to the enthalpy at 1 plus the amount of energy that was put into the fluid by the pump. And so 376.92 is the enthalpy at state 1, 10.3 is the work put in by the pump, and so that's 387.2 kilojoules per kilogram is the amount of energy that is actually at state 2, or its enthalpy at state 2. So Q then is the difference between these two, 3425.1 minus 387, and so the heat that's actually added in the boiler is 3037.9 kilojoules per kilogram, and it's positive because it's heat added to the cycle. Now the reason why I say, as far as your overall error is concerned, it wouldn't make a whole lot of difference whether you used the enthalpy of 2 equal to the enthalpy of 1 and it kind of ignored the pump. The only problem is that you would likely find one of the answers on the exam, one of the answers to be 3047 are roughly 3048 in there, because it would be what is called a distractor, and it would be a very common mistake to ignore the work of the pump. And so anytime that you find two answers that are real close together, you have to be real suspicious on the exam, because one of them is likely to be right and one of them is likely to be wrong by ignoring something like the pump work here. So even though the pump work is small, you need to add it in so that you find the enthalpy at point 2. And I would not be a bit surprised in some of these exam problems if a number like 3037.9 or 3038 is probably what it would be on there, and then there would be another answer that would be 3048 that would be the answer by ignoring the pump work. So this is just a commentary that you want to try and make sure that you get all these answers filled in and do a correct analysis around the cycle. And again, note the QB is positive because it's heat added to the cycle. Okay, let's go now for cycle efficiency. Cycle efficiency is net work over the heat supplied, and the net work over the heat supplied is work of the turbine minus the work of the pump divided by heat added in the boiler. Again, net work is the difference between the two. We just commented a while ago that the pump work is relatively small compared to the turbine work. However, it is not insignificant and should not be ignored in the efficiency equation. So 1061.8 minus 10.3 over 3037.9, the heat of the boiler, gives us a cycle efficiency of about 35%. Net work over the heat supplied. Okay, the next thing we want to do is power output of the boiler. Let's assume we've got a mass flow rate of steam of 100 kilograms per second. And so kilowatt outputs would be m dot times the work of the turbine. So you got 100 kilograms per second times 1061.8 kilojoules per kilogram. Canceling the units here, kilograms and kilograms gives us kilojoules per second. Joule per second's a watt, kilojoule per second's a kilowatt, and so the number of kilowatts are 106,180. And then if we want to convert kilowatts to megawatts, again the relationship, you divide kilowatts by 1,000, and so you'd end up with about 106 megawatts. So this is a small power plant, about a 100 megawatt plant, and lots of these little 100 megawatt plants around, and particularly in municipalities and cities that have the fairly small power plants. Okay, the last thing that we want to illustrate with this problem is isentropic efficiency. And isentropic efficiency is a comparison to sort of an actual efficiency, actual operation of the turbine compared to the operation under ideal conditions. And so we set up this problem to begin with saying we've got an isentropic expansion from 3 to 4, and that expands into the mixture region. So we had to go through and calculate the ideal enthalpy if we had an isentropic expansion, which we did for part A of the problem. Now, the isentropic efficiency, however, it deals with the efficiency of the actual expansion of the turbine compared to the theoretical expansion of the turbine. So it's efficiency involving HI minus HE over HI minus HES. And so isentropic efficiency says how well does the turbine approach isentropic conditions. And in this particular case, we're saying instead of expanding isentropically and reversibly down to 0.4s, the expansion really takes place irreversibly down to saturated vapor condition corresponding to 70.14 kilopascals. So we go to saturated vapor condition for the actual exit out of the turbine can be found at the saturated vapor condition at 70.14 kilopascals, and so that turns out to be, if you look back in your table on page 48, that is 2660.1. H3 is 3425.1 is our state entering the turbine, and the theoretical efficiency then, H3 minus H4s, is the 3425 minus the 2363.4 that we calculated as the isentropic expansion through this particular condition. So if we do that, we get an efficiency of 0.72, which gives us the isentropic efficiency for the turbine.